for coming to tonight's presentation and braving the rain. We were hoping for Santa Barbara sunshine, but it would not have been possible to have this evening without the support of Luke, the CEO and president of the Natural History Museum, and also Allie Coakley, who did so much work to get this all organized. So we're really grateful to them. And as Luke said, we want to recognize our co-sponsors, the Bren School of Environmental Sciences at UC Santa Barbara, and the Community Environmental Council of Santa Barbara. Now, finally, I'd like to point out the significance of today's date. You all know, I'm sure, that this is Earth Day, but the background is rather interesting. About 10 miles from where we're sitting and standing right now, in 1969, January 1969, there was a large blowout on an offshore platform, and a huge amount of oil was spilled. It was the largest oil spill in the United States up until that time. In December, Senator Gaylord Nelson came out to inspect the damage, and he was so impressed with it that he went on to organize the first Earth Day in April 22, 1970. And it took place at college campuses around the United States. And it's estimated that it was attended or observed by 20 million people. That same year was when the Environmental Protection Agency was formed. So I think there isn't a more appropriate time to discuss the important threat to the planet from global warming than today. So I'm going to start by summarizing some of our major concerns about global warming, and then Bill will follow with some of the evidence that we've seen that concerns us. And then I'll follow with some description of consequences, and Bill will then summarize our action plan. So what is a problem, and where are we today? So I'd like to jump ahead a little bit and tell you about our conclusions. First of all, the main conclusion is that global warming is irreversible. You may have people tell you that that's not true, but as Bill and I will show you, it is true. And there's nothing that we can do about it in our lifetimes. And in fact, there's very little that you can do about it in your lifetimes. We can't undo what we've done over the past 175 years in terms of putting greenhouse gases into the atmosphere. Another concern we have is latency, the delay between cause and effect. Problems that we cannot even anticipate may be occurring decades from now. So we will not reach net zero in 2050, as the Intergovernmental Panel on Climate Change, the IPCC, has been recommending, so that we maintain the Earth's temperatures within reasonable limits. The Earth's average temperature is going to keep increasing. It could reach 2.2 degrees centigrade or 3.5 degrees centigrade, 4 to 6 degrees Fahrenheit by the end of the century, according to the IPCC. But we can and we should slow that temperature rising. So global warming is irreversible, as I said. And the reason for that is what you put in the atmosphere stays there for a very long time. We can speed up global warming by putting more greenhouse gases in the atmosphere, but we can't slow it down. To use an automobile analogy, there's no brakes and there's no reverse gear. The problem is, even if greenhouse gases stop tomorrow, the warming that is resulting from the greenhouse gases in the atmosphere already would continue. The warming is not going to stop until greenhouse gases are removed from the atmosphere over a period of time of hundreds of years by natural means. Each year, the IPCC prepares a status report on where we are with reductions of greenhouse gases. This chart is based on commitments made by about 200 countries at the 2015 Paris conference. The red line shows what their combined commitments amount to as originally proposed and as periodically revised. As you can see, that red line is not going down. The IPCC experts also make an assessment of the individual countries' contributions, and they decide what the probability is that each country will do what it committed to do. Some will do more, some will do less, and that shows up in these shaded areas, the pink and orange. Only under very optimistic conditions would the greenhouse gas emissions fall as shown in the blue and green curves going down. And even at that level, with very optimistic assumptions, we won't reach net zero by 2050. And temperatures will not be less than 2 degrees C or 1.5 degrees C until the end of the century or later. So why is this problem so hard to solve? Most people are not directly affected. You think of us sitting here in Santa Barbara, for example. What evidence do we have of global warming? Well, we've had some incidental flooding of coastal areas. Maybe we've had a few more intense, more frequent wildfires, but nothing really that would get our attention. Not like Asia and Africa, parts of Asia where whole coastlines have been flooded, causing people to lose their homes, or Africa, where droughts have caused mass famine and migrations. Another problem is that the government institutions that we have may not be capable of doing what's needed, and Bill's going to address that more specifically. Obviously, we can't do it alone in the United States or in any country. There has to be global cooperation, and particularly among the big players, the China, India, Russia, and the United States, and so on. That cooperation is not going to be easy to achieve. Another problem is opposition and misinformation by climate deniers. What do the deniers say? Well, they say global warming is natural. It's not human caused. Over the eons, the Earth's temperature has gone up and gone down. They say we can't give up fossil fuels. It's too difficult, too expensive. Renewable energy can't provide the energy we need. And maybe we can adopt to a warmer world. Maybe we can figure out ways to mitigate the consequences of warming. And another thing is they say, well, new technologies are going to bail us out. We just have to wait till they come along. And one of the favorite ones is to say, carbon capture. We can suck huge amounts of carbon out of the atmosphere and bury it in the ground. We'll talk more about that later on. So when you look around and you see that every year temperatures are going up and increasing, and global emissions are increasing, how can we ignore that? How can we ignore the warning? Another problem is that for people in the United States and developed countries, climate change is not a high priority. This is a survey done by the Pew Research Corporation. They do this every year, and this shows that among American voters, the strengthening the economy was the top priority. 75% of the people rated it number one. Concern about climate change was rated number 17. And this is down from last year's survey where climate change was rated number 14. So we feel that educating the public is a very critical part of trying to do something about this problem. And it's one of the reasons that Bill and I have written dozens of articles and 2 books. How do we stop global warming? Well, to stop it, ultimately, we have to reach net zero. Net zero is when there's no additional greenhouse gases added to the atmosphere. And practically speaking, it's sort of an impossibility. There's some forms of greenhouse gas emissions that are going to be very difficult, if not impossible, to eliminate. An example is jet fuel for aircraft. You need to find some substitute for that, and that's not going to be easy. So emissions that can't be curtailed have to be offset by some natural means, like absorption on the earth and soil, or capture by trees, and so on. Carbon removal on a very large scale is not practical and not feasible today. So I want to go back to this for a minute. So last year, the world emitted 54 billion metric tons of greenhouse gases, a new record. And it's on the road to set another new record this year. 54 billion metric tons. That's a number that is impossible to visualize. We tried to find a way to convey the significance of that and develop this little picture with all the elephants. Now, in this picture, each elephant represents 10 million African elephants. So the total, 150 million African elephants, has a combined weight equal to 1 billion metric tons. And we're talking about 54 billion metric tons. So it's too late to limit global warming to 2 degrees centigrade. This is the chart that appeared in the first edition of our book, and as we updated it for the current edition. And unfortunately, it didn't change very much in 3 years. The top dashed red line shows what we call business as usual. This is the way emissions are going to continue to increase with growing population, increasing affluence, more energy use, without some significant ways to reduce greenhouse gas emissions. The green line is what would have to happen today to meet the Intergovernmental Panel on Climate Change goal of reaching net zero by 2050. It's clear that that's impossible. That's not going to happen. The blue line is what we think is possible by measures that are known today, that are practical, that are economic, and things like increasing electric vehicles, more energy efficiency, more new devices like LED lighting that use less electricity, and more solar and wind power, and so on. That doesn't get us to net zero by 2050, as you can see. That brings our emissions down to about the level they were in 2005. But it's a positive move, and it buys time for us to do things in the future. Okay, Bill, you're up.
So thanks for being here. Craig memorized his presentation, I didn't. Yes, global warming is real, but there are a lot of people and a lot of organizations that don't want you to believe that. Craig and I have based our conclusions on what we call hard physical evidence that can't be refuted and shouldn't be ignored. Greenhouse gas concentrations in the atmosphere are increasing steadily. The Earth's temperature is also increasing steadily. The ocean's temperature is increasing. The sea levels are rising. Glaciers are melting everywhere. Sea ice is retreating in the Arctic and the Antarctic, and the massive ice caps in Greenland and Antarctica are melting. The Earth's climate can be measured or estimated going back as far as 850,000 years. Past changes were driven by the Milankovitch cycles that determined the Earth's distance from the sun and angle relative to the sun. A full cycle takes about 100,000 years, a very long time, as you can see by the red arrows on this chart in the center of the figure. Also, until recently, carbon dioxide concentrations in the atmosphere, the Earth's atmosphere, have never exceeded 300 parts per million. However, as you can see on the extreme right, where we are today, that the carbon dioxide concentrations today are about 424 parts per million. That's a 40% increase in about 150 years. This increase happened very suddenly on the scale of this figure, much too fast to be due to natural causes. Most of the greenhouse gas emissions, about 75%, are due to our use of fossil fuels, coal, oil, and natural gas, to produce the energy we need to support our modern lifestyles. You can see from this chart that the fossil fuel, global fossil fuel use has very closely paralleled global population growth. This rapidly growing use of fossil fuels directly resulted in a corresponding increase in the atmosphere's carbon dioxide concentrations. Actions to date, and you've heard a lot about what's been done, have not led to any reduction in greenhouse gas emissions. Population growth and per capita energy use due to our higher or rising living standards have, this is the red arrow on our chart here, have offset any reductions. You may have heard that the U.S. has actually reduced its greenhouse gas emissions, and that's true. However, most of this reduction is due to fracking. abundant and low-cost natural gas produced by fracking has displaced coal as the main fuel to produce electricity in the United States, and this has reduced our greenhouse gas emissions. The increased use of solar and wind is also significant, and electricity from solar and wind now the electricity produced using solar and wind now exceeds that produced by using coal in the United States. This is what I call the scariest chart in our presentation. What it shows is that 10 of the hottest years ever recorded were in the last decade. That's batting 1,000, 10 for 10. Last year, 2023, was the hottest year on record, and you can see that in the black line, it broke that record by a wide margin. 2024 is even hotter. March 2024, last month, was the 10th month in a row that broke a temperature record. There are contributing factors, like people tell you, well, last year was an El Nino year, and that's true. However, most of this rapid increase is yet to be explained. It'll take a few more years of data collection to determine if the 2023-2024 period we're in right now is an isolated event or is the start of an ominous new trend. We hope it isn't. It shouldn't be any surprise that in 2023, the ocean temperatures also set a record. And so far, as you can see in the little black line on the left there, ocean temperatures in 2024 are significantly hotter than they were last year. So 2024 is well on the way to become an even hotter, set a new record for the ocean temperatures. According to Berkeley Earth, a very good source of information, the Earth's average temperature is now 1.4 degrees centigrade, or about 2.5 degrees Fahrenheit, higher than it was at the start of the Industrial Revolution in the U.S. when our fossil fuel use really took off. And this baseline, the start of the Industrial Revolution in the U.S., is considered to be the average temperature between 1850 and 1900, and that's a pretty standard baseline for measuring global warming. It's also no surprise that the land is heating up faster than the ocean, because the ocean has a much larger capacity to absorb the heat produced by global warming. And the ocean's average temperature is up 1 degree centigrade. This is another scary chart. Craig and I view the Arctic and the Antarctic as what we've referred to as canaries in the global warming coal mine. They're early warning signs. Rising temperatures in the Arctic have a very big effect on weather in the Northern Hemisphere. This figure is a world heat map that is produced by NASA and updated periodically. We can see that the Arctic is heating up 2 to 4 times faster than the global average. The albedo effect, as it's referred to as the albedo effect, is contributing to a more rapid warming of the Arctic and the Antarctic. Ice and snow reflect about 90% of the sun's radiation. However, dark ocean or bare earth absorb 90% of the sun's radiation. So as ice and snow cover decline in the Arctic and the Antarctic, they absorb more heat from the sun's radiation and they heat up faster. And this is referred to as a positive feedback effect. The melting of the ice caps in Greenland and Antarctica are probably irreversible events at this point. In the past, snow and ice that was lost during the summer months in those regions was easily made up by new snowfall and ice formation in the winter months. Today, the losses of snow and ice in the summer is not offset by new ice and snow in the summer. And this will continue as long as the Earth's temperature is elevated. Another physical sign, again, irrefutable, is that global warming is causing the sea level to rise. So far, the average on a global basis is about 10 inches. This is due to two effects. One is melting ice, putting more water in the ocean, and the other is the thermal expansion of the water in a warmer ocean. Ominously, the rate of increase has doubled in the last 10 years to about 1.8 inches every 10 years. The U.S. National Oceanographic and Atmospheric Administration, NOAA, has a forecast that the sea level rise will be about 2 feet by 2100.
So Bill has explained some of the symptoms we're seeing of problems, and I'd like to talk a little bit about the consequences. First of all, where are we headed right now? This shows the cumulative temperature since the late 1800s up to the present time. This is the average Earth temperature increase, the average increase. It's not the actual temperature of the Earth, it's the average increase. So you can see that in the late 1800s, it was about a half a degree, plus or minus a half a degree centigrade. Commencing in about 1900, though, the curve starts to go up as we began to use fossil fuels, and those were coal for transportation, coal for industrial heating, and coal for generating electricity. That trend continued until the mid-1940s when there was a spike due to World War II. And after that, the rate of increase flattened out as the world economy slowly recovered from the effects of the war. But then again, with the resurging economy, you can see how the curve started going up again as more and more greenhouse gases were emitted, now not just from coal, but from oil and natural gas as well. If you extrapolate this curve from the present time, you can see that we would reach 1.5 degrees centigrade in about 8 years. Actually, it's possible we could reach it in a couple of years because we've had points, as Bill mentioned earlier, at 1.4 degrees centigrade already. And continuing, this would reach 2 degrees centigrade by about 2057. So where do the greenhouse gases come from? Carbon dioxide accounts for 3/4 of greenhouse gases. About 2/3 of the carbon dioxide comes from industrial processes and generating electricity. Another 11% or so comes from uses in agriculture and other uses outside of industry. Methane accounts for about 16% of greenhouse gases. Methane comes from natural gas leaks, flaring of natural gas as part of the production process for oil, and from what we politely call cattle digestion. There's another way to describe it, but I won't do that. Nitrous oxides come primarily from agricultural fertilizer, and the last 2% or so is fluorinated gases, which are from industrial processes and from refrigerants. What happens to carbon dioxide produced on Earth? Well, 30% of it goes into the oceans, absorbed in the oceans. Another 30% is absorbed on land in plants and earth. And only 40% of it goes into the atmosphere. Fortunately, it's not more than that. Of the sun's heat on the Earth, 90% goes into the ocean, warming the oceans. About 8% warms land and melts ice. and about 1% goes into the atmosphere. So that, again, is a fortunate situation because the huge heat sink of the ocean, without it, the Earth would be much warmer. As another consequence of carbon dioxide being absorbed in the ocean, that is, it interacts with seawater and forms carbonic acid. Carbonic acid is destructive of coral reefs and certain forms of sea life. Who produces these greenhouse gases? Well, up until 2005, it was us. It was the United States. We were the leader. For 140 years or so, and in fact, a good fraction of the inventory of greenhouse gases in the atmosphere at the present came from the United States, and a smaller part from the United Kingdom. We were passed in 2005 by China, and so today China total emissions are almost 16 billion metric tons per year, greenhouse gases. The U.S. follows that with 6 billion metric tons. However, the U.S. still retains its leadership in another category, and that is in per capita emissions. The U.S. per capita emissions are about 18 tons per person, 18 tons for every one of us in the country. China follows that with 11 tons per person. The global average is 6.8 tons per person. So the U.S. is producing per capita about 2.5 times the world average. So we have room to improve. What are some of the consequences of global warming? Bill mentioned a number of the trends and things that are happening. Temperatures increasing, sea level rising, ice melting, and so on. But the real consequences of those events are what happens to people. We're experiencing heat waves, forest fires, droughts, public health effects, infrastructure damage, and rising poverty. This is really a human rights issue. There are those who will suffer the soonest and the most are the world's poorest. Another concern we have is tipping points. A tipping point is when in some process is going along and it reaches a certain point where it changes drastically. It accelerates or effects become more severe or something like that. And tipping points are typically not predictable. A couple of examples. I think everyone in here has probably read about forest fires in the Amazon and the problems with cutting down the Amazon forest to create land for ranches and for cattle raising. The Brazilian scientists are very concerned about this, and if this trend is not reversed in a few years, their worry is that the Amazon rainforest will be converted to a savanna. And what that will do is have drastic effects on the weather in the northern hemisphere, less rainfall and more droughts in many critical areas. Another one has to do with ice melting. So you have the land ice in Greenland and in the Antarctic, ice supported on the land. And it's held there in part by floating sea ice, which keeps it from sliding off the land into the ocean. Well, what's happening now is the warmer ocean is slowly attacking the sea ice and causing damage to it. And it raises the prospect that if enough sea ice is damaged, you could have massive blocks of ice on land move into the ocean. And you have to remember that sea ice is floating in the ocean already, so it's not going to raise the sea level. But millions of tons of land ice would raise the sea level. So also, we know what needs to be done. It's not a mystery. There are dozens of studies, plans of how we can deal with global warming in California, in the United States, in the United Kingdom, and in the world. Here's just a short listing of a few of them. The problem is we lack action. We need action. Bill will now talk about the action we think should be done.
Craig and I have studied a lot about what we need to do. We sort of boil it down for simplicity into an action plan that highlights the things that have to be done. And the actions listed on these slides are not optional. If we're really serious about doing something about global warming and climate change, we have to do these things no matter how difficult or how expensive. They're not optional. First, and the easiest, is improving energy efficiency and conservation. It's improving now, but we can do a much better job. This is the low-hanging fruit. Improving efficiency and conservation reduces our future energy needs significantly without affecting our lifestyles. This could reduce the amount of energy we need by our guess or estimate by about 25% over the next 30 years or so. Second, and the biggest and I'd say the most difficult change is to produce all of our electricity using renewables. That is displacing coal and natural gas with solar and wind and possibly nuclear. We'll cover that a little later. To do this, an essential project is to upgrade and modernize the nation's electrical grid to distribute about 300% more electricity than we're producing today. It's a big change. And also to connect the best locations for renewable energy production with the grid. It doesn't do any good to build a solar farm if you can't get a grid connection. Today we have thousands of renewable energy projects across the United States that are waiting for grid connections. Third, we have to use electricity instead of fossil fuels wherever it's possible to produce the power and heat we need for industry, for commerce, and for our residential uses. Fourth, we need to convert our transportation system to electric vehicles. Fifth, the processes that can't be electrified, an obvious one would be airline travel. There'll be a need for synthetic fuels, and it's certainly practical to produce drop-in replacements using recycled carbon dioxide. It can be done, but you'd have to do that. And there is a possibility that substitute fuels, such as hydrogen made from by electrolysis using electricity from renewables, could also become a practical alternative fuel. Sixth, as Craig mentioned with the Amazon, we have to stop deforestation and really plant billions of trees. We have to restore some of nature's ability to remove carbon dioxide from the atmosphere. Seventh, many of our agricultural processes and practices have to change. This is to reduce methane and nitrous oxide emissions. And then finally, we stress this, we need a smooth transition. If we go around shutting down coal, oil, and natural gas supplies, as some people want to do, before we have reliable renewable energy to replace the fossil fuels, we'll have chaos. We'll have brownouts, we'll have blackouts, and we'll have big increases in energy prices that will be probably intolerable to the general public. What should the government do? It's not what they're doing, it's what should they do. Present government efforts are based on legislation. That is basically mandates, subsidies, tax breaks, and all of this is spending borrowed money. The purpose of this is to provide incentives to transition from fossil fuels to renewables. We believe these efforts will not solve the problem, but they will make some progress, but at a very substantial expense. We are proceeding without an overall organization. No one's in overall charge to manage the transition, and we don't have an overall implementation plan. A comprehensive implementation plan, in our minds, is needed with a very realistic estimate of how long it's going to take to get to net zero, what it will cost, and who pays. In our opinion, an organization like the Department of Energy, they're already in place, could be tasked with preparing a plan involving other government agencies, our universities, and the private sector. Finally, we should stop subsidizing fossil fuels and ethanol. Subsidizing fossil fuels delays the transition from fossil fuels to renewables. A very effective tool would be to implement a carbon tax. That would be very effective, but today we consider that to be a political impossibility. An argument that you will often hear is that we can't afford to do this. The transition to renewables will just cost too much. It'll cost trillions of dollars. We can't afford it. We disagree. In 2023, global energy investment was a massive $2.8 trillion 1 year. And already over 60% of this money was spent on renewable energy projects. The transition to renewables will take a long time, in our opinion, perhaps 50 years or more, during which time global energy investment will exceed, let's say, $140 trillion based on just straight arithmetic. Most of this investment would be to replace obsolete fossil fuel infrastructure that's at the end of its design lives. If we don't replace this infrastructure with fossil fuels, we could spend it on renewables, and there'd be sufficient funds for what needs to be done. Also, if essential infrastructure is put in up front, most of this investment that was required would be funded by the private sector, not by deficit-financed government spending. Finally, studies do show that the cost of living with global warming long-term is exceeds the cost of dealing with global warming in the same time period. Another frequently heard concern is that electricity from renewables costs too much. It'll be too expensive. And unfortunately, it's true if you live in California. But we don't believe that actually greater use of renewables need not increase electricity prices. And this is a real-life demonstration in Texas. About 10 years ago, the Energy Reliability Council of Texas, ERCOT, which runs the Texas grid for almost all the state, completed a $7 billion transmission system expansion. And this expansion was to connect the sunny and windy areas of the state in Texas with the major cities. What resulted was a private sector boom in solar and wind projects, all privately financed. Texas now leads the nation, the U.S., in electricity production from renewable sources, as well as leading in oil and gas production. A very important part of what Texas did was they deregulated their electricity market and introduced true competition between electricity suppliers. As a result, Texas today has among the lowest electricity rates in the country. The average electricity rate in Texas is about 11 cents a kilowatt hour, and the average for California is almost twice that much at 20 cents a kilowatt hour. It's not all bad news. Craig and I have said for a long time that what we say is the trend is our friend. Renewable energy, solar and wind, is now the cheapest form of energy in many parts of the world, most parts of the world, and it's getting better every day due to new technology and improving economies of scale. Batteries that have been lagging for a while, battery technology, is improving dramatically. That's in cost improvements and performance improvements, and that'll be improving our ability to store energy. Auto producers are transitioning to electric vehicles, and there are several large projects, some in the US, some in California, that are demonstrating that renewable energy is a practical alternative to fossil fuels. A big benefit that is in limiting fossil fuel use or reducing it is that we eliminate most air pollution, a big plus. Something that's frequently discussed, more frequently discussed today, is what about nuclear? And we think there's a lot of what we would refer to as happy talk about the need for nuclear power and how wonderful it would be to help us reduce global warming emissions, greenhouse gas emissions, rather. And Craig and I, as Luke said, we spent part of our career in the nuclear power industry, and we're reasonably familiar with that industry. And we can say nuclear power works, and it can be a safe and reliable source of electricity. But we in the US have let the nuclear power industry die for several reasons. And reviving nuclear power today would take a very long time, be very expensive, and may not be successful. Also, we have to remember that nuclear power is emissions-free, but it is not waste-free. Depleted fuel rods contain a lot of very toxic material that has to be safely stored essentially forever. And we have yet to agree on a politically acceptable solution to this nuclear waste disposal problem. Also, the task would be monumental. Today we have 93 nuclear reactors producing about 18% rather, of our electricity in the United States. The average age of these reactors is over 42 years old. They're all getting to the end of their service lives and will have to be replaced just to maintain our current nuclear electricity generation. And we think this will cost up to $1 trillion just to replace today's operating reactors. And finally, nuclear power has to be cost competitive with the alternatives. Today, the competition is electricity produced using natural gas, and increasingly it will be competing with electricity produced by renewables with battery storage. China's on everybody's mind from time to time, and there's a China challenge. China is the world's largest emitter of greenhouse gases, as Craig mentioned, overtaking the United States in 2005. This is all, China needs to reduce its fossil fuel use for several reasons. It has a terrific air pollution problem. If you've ever been to China, I've been to a lot of time in China, the air pollution is unbelievable. The other thing is China does not have the US fossil fuel reserves, mainly oil and gas. They have coal. So they have to import their oil mostly from the Middle East. And so there's a national security issue as they want to be more energy independent and replace fossil fuel imports, and renewables is a way to do that. And the third is to obviously reduce global warming or reduce greenhouse gas emissions. On a positive side, China actually leads the world in renewable energy. Most people don't know that China is the world's largest user as well as manufacturer of solar panels and wind turbines. They also lead the world in the production of electric vehicles, batteries, high-speed rail, and nuclear power plants. China has 25-year plans for certain critical industries, And one of the areas they have targeted is to be, they think of global warming as a major business opportunity, and they want to lead the world as being the world's leading supplier in things like solar, wind, and nuclear, and other technologies. And they're well on their way to accomplishing this objective. So how do we think this is going to play out? What might happen? Craig and I have made a prognosis, and this is based on a very cloudy crystal ball, obviously. We are attempting to be realists. We don't want to be optimists or pessimists. We believe we're moving in the right direction, but we're not moving fast enough, and we need to expand the scope as well as the speed. As Craig mentioned, we believe it's way too late to limit global warming to 2 degrees centigrade. We certainly will not reach net zero by 2050, the government objective. We also believe that without a national plan and an organization to manage the implementation, we will have to stumble forward with setbacks as well as successes along the way. Transition problems and possible cost increases in our mind will be discouraging to the average citizen, and they could come to doubt the wisdom of transitioning to renewables. The climate deniers, those who are opposed to doing anything about global warming may be able to claim that they are being vindicated. We also feel that a major unavoidable and big expense is going to be the cost of adapting to higher global temperatures and to mitigate their effects. This is unavoidable no matter what we do. We've already baked a lot into the cake. On a positive side, technology is moving forward, and economies of scale are improving for renewable energy. And we feel that renewables, as they are today, will increasingly displace fossil fuels, but it may be a slow process. I think we have a big risk of becoming dependent upon China for much of our green energy products and technology. If so, it'll be our own fault. We've let them get ahead and stay ahead. We can't blame China for that. We could exceed one or more of the tipping points that Craig briefly discussed earlier. Exceeding a tipping point could be a global wake-up call that we need to just say, okay, we really have to do something about global warming. So far, we haven't had the equivalent of a 9/11 or Pearl Harbor or something like that that says you've got to do something about this. The worst case, exceeding a tipping point, could lead to an acceleration of global warming or climate change, and something that we can't do anything about, which is an acceleration of the problem. We believe that over time, we could reach net zero sometime in the future. When, we don't think it's possible to make a forecast today. And then we keep reminding ourselves and others that failure is an option. There's absolutely no guarantee that the world will ever reach net zero, and we'll have to live with ever-increasing global temperatures and climate change. Craig and I are optimists. We think that we can do something about this problem. We should, and we hope we do. One question is, what can you do? I think one thing they have to keep in mind is that the small steps, no matter how commendable they are, aren't going to do it. If we don't do the big things, such as electrifying the economy and building a modern national electric grid, then the small things just won't make enough of a difference. And I'd say that perhaps the biggest thing that you could do is spread the word. Educating the public, as Craig mentioned earlier, and getting their support is a much needed first step to doing the big things that need to be done. And that's why Craig and I have researched this topic, written books and articles on it. So that concludes our presentation. The presentation will be posted for those who are interested on our website, theglobalclimatecrisis.com, along with some other material, and we also thank you very much for being here.
Thank you. We're going to have some questions and answers, but first there's one other announcement I wanted to make. In our book, we have 6 special studies made by experts writing about special topics like advanced batteries and so on. And 3 of those authors are here tonight. I'd like them to stand and be acknowledged. So Dr. Kelly Parmenter, somewhere here. Oh, there she is. And Dr. Magdi Farhat, somewhere. There he is, all right. And Mr. Robert Taylor. Hey, all right, thank you very much. How are we going to handle the Q&A?
So I'm Rosina Garcia. I'm the Director of Education here. Just raise your hand and I'll run over to you so you can ask your question. Any takers?
Just thank you for your presentation. A couple of points. One idea that has been being put somewhat into action, but certainly could see more, and that is that a lot of industry their need is just for heat, and they're using fossil fuels for that. And the idea of having standard little nuclear reactors that have a standard design, so they only have to be approved once, could be made like at a factory and brought to those places, and they're very small, so they don't really present a huge risk, would be one way to satisfy cutting down fossil fuels and turning it using nuclear power plants. And the other thing that's on the good side. On the bad side, we also have things that cannot be replaced by having solar energy or wind, and that is the gases that are produced in the actual production of steel and cement are a fair amount of percentage. It's maybe like 10 or 20% or something like that, but you can't get it to go away that way unless you find new processes, new chemical reactions to actually produce those products. So do you have any comment about attacking those?
You asked 2 questions, and I'll cover the nuclear one first. So Craig and I have written a couple op-eds on nuclear. What? Oh, okay. Can you hear me now? Yeah, we've written an op-ed on nuclear power. We have a draft paper that we're going to try to get published. And this is what we refer to as the happy talk. Small modular reactors are being talked about today as being wonderful because we can build them in a factory. They're small enough so you can transport them on a truck and to a site and put them in. One thing, I was in the nuclear Navy. The Navy's been building small modular reactors since 1954 with the launch of the Nautilus. So that in itself is not unique. And there's a lot of things that aren't addressed there. And there are some small modular reactor projects that have been canceled recently because they're too expensive. And the fundamental thing is big nuclear power plants, like 1,100 megawatts, cost billions to build. But if you build 100 small ones, the economies of scale don't work in reverse. And so I have a strong suspicion that they're going to be way too expensive. The other thing is that people are proposing that. They're saying, gee, we can take them to where there used to be a coal-fired power plant. You've got the electrical switchgear there, you've got all the stuff. You just take out the coal plant, dig a hole, and put a small modular reactor there. It's not that simple. The biggest issue, one of the biggest issues that killed nuclear power is public fear of living near a nuclear power plant. And you have to convince the public that they're safe, and putting small ones is not going to take away the public concerns about nuclear safety. And if you wanted to build small modular reactors, you have to start by building workable prototypes and test them for their performance, their safety, their economics. And we haven't even started on small modular reactors. All of these attributes are based on paper designs. And nuclear power has always cost a lot more than anybody ever estimated. So even if it works, it's going to take a long time. And I think you're going to have a hell of a time replacing the 93 big reactors we have. And if you say, let's do it by having 100 megawatt reactors instead of 1,000 megawatt reactors, you've got to have thousands of sites, not hundreds. So I think there's a lot of things that people gloss over when they talk about the wonders of small modular reactors. That may be more than you want to know. But yeah, go ahead.
Yeah, I'm not sure I heard the last of your comment there, but I believe you said, talked about the emissions from cement and steel production. And that was a very good observation, because cement and steel are two of the critical building materials that are used all over the world and are responsible for a significant amount of greenhouse gas emissions. There is some rays of hope in terms of finding processes that don't require natural gas, using hydrogen and to produce steel, using different methods to produce cement. So there may be things to be gained from new technology, new processes on those particular materials.
They may also be one of the things that have to be offset. What? They may be one of the things that have to be offset.
Oh.
Yes.
Yeah, Bill points out that if we don't find ways to do that, then that's going to be another source of carbon emissions that we're going to have to find a way to offset somehow.
Thank you. Any other questions?
The idea of a carbon tax isn't new, but you mentioned that it may be politically not acceptable. Could you elaborate on what the political problems would be?
Political problems of the carbon tax?
Yes.
Could you repeat that?
Can you elaborate on political problems with the carbon tax?
The problems with the carbon tax. Actually, about 50 countries have some form of carbon tax. Some in Scandinavia have a very high carbon tax of like $100 a ton. Other countries go down from there to $1 a ton, for example. In the United States, before the 2016 elections, there was a bilateral move by Congress to create a carbon tax. It was supported by Republicans and Democrats. It didn't get passed, and then with the election, a number of the people who in Congress who supported it, unfortunately did not get reelected. And so it died, and it's still, I guess I would say, moribund. There doesn't seem to be any political will to do that in the United States.
I think we have time for 2 more questions. Ooh, whoa, okay, all the hands went up.
Do you see any feasibility of a solar farm near the city of Santa Barbara? Is there any place we could put a large solar farm? with the transmission that would be necessary.
Are you saying, are there opportunities to put large solar farms near Santa Barbara?
Yes.
Yeah, Craig might have some things to say. I mentioned that's raised a very big issue, and I mentioned siting with nuclear power, but the same thing applies to solar and wind. There's a lot of places in the United States that are ideal for solar and wind, like West Texas. And I don't think you have to put them in places where they'll be objective by the general public. I mean, that's a big issue. I have friends that have a farm in Michigan, and some of their neighbors are leasing land for wind turbines. And so you're taking farmland and putting wind turbines up there in Michigan, and there are people who are thinking about putting solar farms in Massachusetts, why not put them, in Canada or something? But I think if you look at it, there are plenty of places in the United States where you have marginally used land that would be great for solar and wind, but it has to have an electrical grid connection. And I also think that that's a long-range planning issue that we're just not doing. We're giving subsidies out and letting individual developers go find a place and put up some solar panels or some wind turbines. And, we're making progress, but that's not the best solution in my mind. And I think if we deal with siting as an issue and not try to put things in places that are unacceptable to the public for good reasons, we have plenty of places to develop for solar and wind. That would be my feeling. Yeah, yeah.
All right, one more question. I saw some hands over here. Oh, yes, you were quick.
If I understood, can you hear me? If I understood, you're saying that by the end of this century, we're going to be facing 2 degrees centigrade increase in temperature, more or less independent of what we do. I mean, the chances are it's going to be 2 degrees Celsius. Can you translate that prognosis into a ballpark range of sea level change that one could expect from a 2 degree Celsius increase of temperature global?
So it sounds like regardless of what we do, there will be at least a 2 degrees Celsius increase in temperature by the end of the century. How does that translate to sea levels and oceans changing?
I'm sorry.
So it sounds like regardless of what we do, there will be at least a 2 degrees Celsius increase in temperature by the end of the century. How does that translate to sea levels and ocean changing?
That's a really good question. We can't predict that. It all depends on, what happens with the Arctic and Antarctic ice, basically. And if the Earth's temperature, the average temperature of the Earth increases by 2 degrees C, that doesn't necessarily mean the Arctic and Antarctic are going to be increasing, although we think it's likely they would be. But the sea level rise really depends on what happens in the North and South polar areas in terms of ice melting. And it's very difficult to predict. I don't know of anybody that would venture to say they can predict what's happening. We can talk about the trends that we're seeing right now. It's possible that they could be reversed, but we don't think so. Okay.
I think we're going to end it with one final question from our CEO and President, Luke.
Thank you so much, guys, and thank you, Rosina. And you touched on it a bit, kind of a move to more reliance on renewable energies and battery backup, it strikes me that a whole host of other industries also need to change how they do things, because extracting lithium for batteries is so incredibly damaging to the environment. That's not sustainable. How we recycle or decommission used batteries right now isn't sustainable. I mean, so you can say there's incredible entrepreneurial opportunities in all these related industries, but everything has got to kind of move along in a broad front. And I'm just wondering if you could comment at all upon that.
That's a common thing, you know, oh gee, you look at, you know, we got all this waste produced by old solar panels or something like that, or we don't have enough copper or lithium. I mean, this has been a history of technology. I mean, Henry Ford, when somebody said, oh my God, this guy's going to invent an automobile and we don't have enough steel. You know, I think a lot of these problems are solvable by over time, and it's not something we have to do tomorrow. And I think the other thing is it's happening. We can say, oh, we're not going to mine lithium here, we're not going to do this, we're not going to do that. China's doing it. Other people are going to do it. And what's the alternative if you don't do it? And so, in my mind, these are problems to be solved, not showstoppers. And I also, I think Craig and I believe strongly that moving to renewables is a big benefit. For one thing, you eliminate most air pollution, just right off the top. And so it's happening. It's going to happen with or without us. And we have to decide what are we going to do, in my mind. I don't know if that's a fair amount.
Yeah, I'll just add a couple things.
Yeah.
So, sorry, Luke, I didn't quite understand your question the first time. But looking at the development, there are a lot of work going on batteries. There are solid-state batteries. There are batteries that don't require lithium. There are batteries that will stay charged for days or weeks. A lot of new developments coming along. And it takes time to prove them out and make sure the costs are economical. There's also a tremendous amount of progress with solar panels, making them thinner, higher efficiency. There are panels that will generate electricity during the day and small amounts of electricity even at night in the darkness by incorporating a thermistor in the back of the panel. So there's a lot of new developments, and I think as these things proceed and we identify problems with raw materials or certain resources, they'll get solved. I think there's just a tremendous momentum to make sure that they get solved. And the same problems were, in some form or another, were experienced 50 years ago in the development of gas turbines and diesel generators and other things. Those technologies have reached the apex of what they can do. They're not going to be improved further. On the other hand, on the new technologies, the developments are just begun, and there's room for considerable improvement. And I'm optimistic that those improvements will come along. So, go ahead.
Yeah. You know, on this issue, we could obviously be here way too long, but a lot of people say, oh, we have to stop because you can't do this, you can't do that. Oh, you know, we have to stop because of this problem or that problem. But we're really dealing with trade-offs. I mean, lithium, using that as an example, which would you rather do, drill for oil or mine lithium? You know, it's not, you can't do both. You can't do any of those. And so I think we have some hard choices to make. And there are ways they can be done, and science, this technology is moving forward, and I think we have to go with it. And I think there's a lot of ways we could do things right. But if we don't have a plan, if we don't organize, if we're going to subsidize things rather than, you know, that instead of having a carbon tax, we're going to raise the cost of a transition and make a lot of mistakes, is my feeling.
Thank you all for coming. If you weren't able to ask a question, you can visit the globalclimatecrisis.com and you can purchase Bill and Craig's book and to learn more. Thank you.